So, up until this point with capacitors, we've talked about capacitors as either on or off, as either a wire or an open circuit, right? And that assumes that it's a wire just as long as you're talking about the instant after you start charging the capacitor, it behaves like a wire because there's absolutely no resistance to charges building up on the capacitor. So it looks like it's a wire. And then after a long time, the capacitor is full, which means no more charges flow, right? So, what we're going to talk about now is not the time instantly after, nor the time after a long time, but I want to know what happens with current in the capacitor, or rather current building up on one side and coming out of the other, for the duration of time when the charge is building up, but not quite full. All right? That's called the transient response. And we've done this before. We first did it with force, right? When we first learned about separation of variables. Then we did it again. I think, when was the next time we did it?
It would be simple harmonic motion.
Simple harmonic motion. Actually, we did it a little bit in simple harmonic motion, but we actually did second order.
Oh, right, yeah.
Simple harmonic motion. Now we're going back to force that same process, but now we're talking about capacitor and resistor circuits. All right, so what we're interested in is the voltage buildup across a capacitor as you start out from an empty capacitor to a full capacitor. I want to know how it builds up. Sound good? All right, let's begin. All right, so in general, a given RC circuit may produce graphs of two different shapes depending on what you look at. The two different shapes, once again, are buildup and decay. What's the equation for decay? Well, that's this one, right? So the equation is the final x value is the initial x value times e to the negative t over tau. That's the decay equation. Build-up equation is just this flipped, right? So build-up is 1 minus e to the negative t over tau. Tau, no. Now tau is something different. Tau is time constant. We are not using the 2 pi definition of tau. Tau is time constant. Time constant was, what was it for force and... Remember when we did forces, we had time constant? It was like m over b or something like that.
Yeah.
Remember that? Or maybe it was b over m. I don't remember. It was probably b over m. Now it's going to be not b over m anymore because we're not talking about viscous friction and or mass. Now we're talking about circuit stuff like charges and capacitance and resistance. All right, so tau is going to be something different, but the form of the equation is exactly the same as it was before. So, assuming you are starting from an initial value of 0, you're going to build up from 0 to your final steady state value. And for decay, assuming you're starting at some initial steady state value and you're decaying to 0. That's what the equations would be. Sound good? All right, let's do it. Separation of variables all over again. All right. Now, time constant is not time constant is not 2 pi. Time constant is the amount of time it takes to get within about 37% of your final value. All right? Or, in other words, 1 over e of your final value. All right. Oh, tau is also not torque. Right? Because tau was torque before?
Yeah.
Right. It's a measure of how long it takes for you to get to where you're going. Tau for simple RC circuits is R times C. Ooh, isn't that convenient? What's R stand for? Resistance. What's C stand for? Capacitance. All right. Simple RC circuits means one resistor, one capacitor. If you have 2 resistors or you have multiple capacitors or something like that, RC, the time constant might no longer be R times C. It might be 1/2 RC, or it might be 3/2 RC. You'd have to figure it out, and that's beyond the scope of this course. We're not going to go there. Sound good? But for simple RC circuits, tau is R times C. All right, let's check units, shall we? Ready to have your head blown?
Yes.
Here we go. Unit check. What's the units of tau?
Second.
Seconds. Tau should be RC, right? What's the units of R? Ohms. What's the units of C?
Farad.
So, did you know an ohm times a farad equals a second?
Um,
I would do, obviously.
Clearly.
oh yeah, because amp is charge per second.
Right.
Multiplied by the volts cancel out, the coulomb
Yeah.
cancels out.
Ohms is volts per amp, because that's kind of the definition of it, which is a volt divided by a coulomb per second. So a volt second per coulomb. And then a farad is coulomb per volt, because that was the definition of farad. Volts cancel, like you said, and you're left with seconds. Good, good? All right, so that, I think that actually has shown up in the past as a multiple choice question. Oh, this is a common thing that some professors do. They do an equal sign with a dot, means has units of. So, resistance has units of ohms. And then you put units in brackets to indicate that it's units instead of some other thing. Good? So, yeah, some people do that. I just thought it's, it's a nice clean way to say it has units of rather than just being equal to. All right, here we go. So, how do we actually determine the time constant of a circuit? Well, let's start with a simple one. Let's say you had a capacitor that's initially charged up. What's it mean? It's got positives on the top and negatives on the bottom. And you have a resistor and a switch that's open. What's going to happen when you close the switch?
Charge is gonna flow.
Which way are charges going to flow? Yeah, you're going to go clockwise, right? All right. Okay, so that's right. Will it keep on flowing forever?
No.
When will it stop?
When there's equal potential everywhere. in the
Right.
circuit.
Does it take 0 time for this to happen?
No.
No. So the current's going to start off flowing like V over R, right? And then end up with 0 current. So the current should decay away, right? All right, what's going to happen to the voltage across the capacitor?
It's gonna decrease.
That should decay away too. Good? All right, so here we go. Let's prove it. So, the reason I have you do all that Kirchhoffs laws practice is because of this. We are going to use Kirchhoffs voltage law, or the loop law, from here on out for the rest of the year. It's going to be our go-to solution technique for determining a differential equation and coming up with an answer. All right? Just like F equals ma was for Newton's laws, Kirchhoff's voltage law is the circuit's version of F equals ma. Sound good? We're going to use it a lot. So we're going to do loops. So here we go. Kirchhoff's voltage law. We're going to write a differential equation for the charge on the capacitor. And then you're going to solve the differential equation. Then you're going to take the derivative of charge. What's the derivative of charge going to be?
Derivative of charge.
Current?
It's actually going to be current. How come?
Because current is charge flowing over.
Charge divided by time, right? So we're going to solve for charge and then take the derivative of it to find the current. Sound good? All right, so let's do it. So the first thing we do in this example is we start with the voltage law. I'm going to start at this point in the lower left-hand corner. What's the first thing I see going around the circle? I see the capacitor. Are you going to gain voltage or lose voltage across this capacitor?
Gain.
You're going to gain. So it's going to be plus the voltage across the capacitor. Then going around, going around, going around, what's the next thing I see? The resistor. Are you going to gain or lose across the resistor? Lose voltage. So it's going to be plus voltage across the capacitor minus voltage across the resistor equals 0. Sound good? All right, so let's write that out. Plus voltage across the capacitor minus voltage across the resistor equals 0. Good so far? All right. Now, if you remember the capacitor equation from yesterday, the voltage across the capacitor is the charge on the capacitor divided by the capacitance, right? Now, the voltage across the resistor, though, is the current times the resistance, right? Now, here's the first trick. Is there a relationship between the current flowing through the capacitor and the charge on the capacitor? What's the relationship? Well, first of all, what's the relationship between current and charge?
Is the derivative of charge.
I equals dq over dt, right?
Yes.
But Justin just made a good point. If this is the direction of positive current flow, what is positive current flow doing to the charge of the capacitor? Decreasing it. So in this case, the current flowing through the capacitor would be equal to the negative dq over dt of the capacitor. Negative because it's decreasing the charge, not increasing the charge. If current flows, the charge on the capacitor decreases. Wouldn't you agree? If current flows from the top side of the capacitor to the bottom side of the capacitor, no, you're starting with a capacitor with positives on this end and negatives on this end. So as that current flows, what happens to those charges? They go from here to here. So there was 4, and now there's only 3, and now there's only 2, and now there's only 1. What's happening? It's decreasing the charge on the capacitor, not increasing it. Does that make sense? This is the key to these problems. You've got to understand it. Ah, yes, we will do problems where charge builds up, but just not this one. That's going to be the next problem we do. All right, so in this case, charge is going to be decreasing on the capacitor if current is flowing. All right, so here we go. Charge on the capacitor divided by the capacitance equals I through the resistor times R through the resistor. But I through the resistor is the same as I through the capacitor. And I through the capacitor tends to decrease the charge on the capacitor. So in other words, we will substitute I with negative dq over dt. So it becomes q over c equals dq over dt times R plus dq over dt times R equals 0. Good? How can you rearrange that equation to make it easy to solve? First of all, what is your variables? Or what are your variables? Is R a variable?
No.
Is the capacitance a variable?
No.
So what are the variables?
Just
Charge and time. So, can we separate them?
yes.
Yes. How? Actually, first thing I did, before I separated them, I put the R and the C together. Because I know I want my R and C to be together in the end. So I just divided by R. But separating the variables, I put the Q's on the left side and the T on the right side, together with the constant. So I got 1 over Q dQ equals negative 1 over RC dt. Then what? Let's
Integrate both sides.
integrate both sides. And you're left with solve, 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 integrate, 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 plug in values, end up with the charge equals the initial charge times e to the negative t over RC. All right, give me thumbs up, thumbs down on your comfort level of setting up and solving this type of problem. Thumbs up, thumbs down. All right, hopefully you're thumbs up, but if you're not, we need to work on it and get you solid because we're going to be doing a lot of these for the rest of the year. Yes?
Why is Q divided by Q?
Because one's the initial value of Q and one is the current value of Q.
But the initial value isn't 1.
What?
You put a Q initial on the other side.
It's Q equals Q initial.
Yeah. Yeah, the initial Q is whatever charge you started with on the capacitor. That's going to change over time, though, according to this equation. Yeah, it's the PERT equation. Same thing. PERT equation. Yeah. All right, so here we go. If we got the Q as a function of time, how do we get the current as a function of time? Take the derivative. Well, the derivative of this is actually really easy, right? Chain rule it out, and you're left with I equals negative Q naught over RC times e to the negative t over RC. That's why we like e's so much, because derivatives and integrals are really easy. All right?
E for easy.
That's right. Okay, so last little piece of this. Basically what you end up with is this graph right here. Current is a function of time. What happens to the current? It goes away, right? As you have less and less charge, there's less and less reason for current to flow, and so the current gets weaker and weaker and weaker. All right? Until eventually, how long does it take for the current to equal 0? Forever. But, how long does it take to get close enough to 0 that we don't really care about it anymore?
Isn't it about 5 time constants? It's 1 over
About 4, 5, or 6 time constants, depending on how long you want it to be. No, actually, 1 over E, you're within 37%. 1 over E squared, you're within like 9%, I think it is. 1 over E cubed, you're at like 5%. And then 1 over E to the 4th. 4 times constants, it's like
3% or 2.
like 2%, I think. And then 5 time constants, like less than 1%. So typically in engineering, you say, or in physics, you say, if you've gone for 5 time constants, you're pretty much there.
But doesn't that capacitance release all its charge like right away? So
The resistor slows it down though, right? So the bigger the resistor is, if you had a huge resistor, how's that going to affect things? It'll be much, much slower. And so you can actually choose also if you have a big capacitor, how does that affect things? No, it's actually slower, right?
It's more charge that holds.
It holds more charge, right? So yeah, if a bigger resistor slows things down, and also a bigger capacitor slows things down as well. So if you want this thing to last a whole second, all you have to do is choose a resistor and a capacitor that multiply those two numbers together that have a value of like 1 second. And you'll have something that decays away nicely, long enough that you can actually see it decaying away. All right, so we actually set up a circuit for regular physics where we did that. We're like, well, I need a resistor that's like 1,000 ohms, and I need a capacitor that's like 0.001 farads, and if you do that, you end up with a circuit that will decay away over like a couple of seconds, and you'll be able to see it decay away, which is pretty cool. Sound good? All right, cool. What about the voltage on the capacitor? All you have to do is voltage is charge divided by capacitance, right? So all you have to do is take your equation that you had for charge, divide that by capacitance, and you have the equation for voltage on the capacitor. So you could be asked either thing. I could ask you a free response question where you're asked give me the equation for the voltage on the capacitor as a function of time, or I could ask you for current through the capacitor or through the circuit as a function of time. Either way. Sound good?
Wait, what did you do? 'Cause where's that?
Oh, sorry. The math for the voltage is right here. So voltage is just charge as a charge over C.
Yeah.
I think she's asking where did you then get the
Wait,
current
and then
over
that was
resistance,
charge.
and then
Oh, how did I do that?
Yeah.
Oh,
What is that?
current divided by resistance. Well,
V equals
I is Q over C, RC, right? So Q over C, RC divided by R is just Q over C. I just combined this equation, divide this equation by I, and you end up with, what's I divided by R is voltage, right? Or you could just take your I equation, divide by R, and it'll also give you the voltage equation. So either way. All right, next one. So that was the easiest one. Let's go to one harder. So what we've done so far is sliding to a stop, right? What's the speed as you slide to a stop? What we're going to do next is starting off at rest and pushing a box until it gets up to speed. All right? What's the electrical equivalent to that? What's going to be pushing the box? The battery. So we're going to hook up a battery to this circuit, and we're going to charge up a capacitor. Is that going to be build up or decay?
build up.
Build up. So the next equation is build up. How do you get build up? You charge up a capacitor with a battery, and the circuit looks like that. All right? So initially, how much charge is on the capacitor?
None.
0. But when I close that switch, what's going to happen?
Charge is gonna start.
Charge is going to start flowing. All right? And then eventually, after a long time, what's the current going to be? 0. So current, once again, is going to, it's going to be decay. It's going to start off like going like crazy and then decay away.
Is that resistor necessary?
Absolutely, because if there were no resistance, how long would this process take?
Instant.
Instant. 0 time. Yeah, it would take 0 time if there were truly no resistance. Now, if there was just a really small resistance, it would just take a very small time. Because once again, it's R times C. All right, so here we go. We're going to do KVL again, the loop law. So here we go. I'm going to start in the corner, the lower left-hand corner, and go around the circuit. What's the first thing I see?
Battery.
A battery. Is that I'm going to gain or lose across that battery? Gain. So I'm going to gain whatever the EMF of the battery is. Then the next thing I see is a resistor. I'm going to gain or lose? Lose. Next thing I see is the capacitor. What, gain or lose? Lose. So the equation is the EMF that you start with minus I times R of the resistor minus Q over C of the capacitor equals 0. Okay, first trick. Now, this goes back to Macy's question. Is positive current flow, or current flow that goes around in the clockwise direction, is that gonna increase or decrease the charge on the capacitor? Take a look. Positive current will actually charge up the capacitor in this case. In other words, that positive current gives you a positive dq over dt on the capacitor. So anytime we see current, we're going to replace it with dq over dt instead of negative dq over dt. So we're left with the EMF minus dq over dt times R minus q over c times equals 0. And what do we do now? We got to differential equationify it, right? Well, it's already a differential equation, but we got to separate the variables. What are the variables that we're going to separate? Q and T. Everything else on here is a constant, but this one is tricky. It's the same level of tricky that you had to do for pushing a box, though, with the same tricks. I'm going to try to get RC by itself on the right-hand side. Or rather, R times C I'm going to try to get together, and then get all the constants on the right side, and then... No, actually, I'm not going to be able to do that, am I? I'm going to try to get Q's on the left, T's on the right. Sound good? All right, let's do that. So, it's going to start off with dq over dt, and then stuff on the right. Then I'm going to go and try to get my RCs together. So here I had an epsilon over R, EMF over R. I want to get that with a C in it. So what do I got to do? Multiply top and bottom by C. So it's EMF times C over R times C, then combine like terms. Got it? So I got my RC together. So I got my 1 over RC on the right side. That's good. Now I also like to have a negative sign. It's just style points if you do it this way, but I always like to do it this way. I always like negative signs in front of my stuff. So negative RC times dt. And if you do that, multiply by -1, these numbers end up switching. Instead of, yeah. Then integrate both sides, do a bunch of integrate, solve. And you're left with charge as a function of time equals EMF times the capacitance times 1 minus -t over RC, just like we would expect with buildup. Yes, Dino?
Does it matter if you multiply by -1 or not?
You either have to do it right off the bat, which I think is cleaner, or you can do it and deal with negative logs. Right? And then you got to remember your log rules, and remember if you subtract the logs, it's the same as dividing and all that. It works out the same either way. It's just you have to be careful. I trust myself more if I don't have to deal with those logs. So I always do it right off the bat. Put a negative in front on the right side. Okay. Now here's an interesting thing. What is this quantity, epsilon, or EMF, times the capacitance equal to? That's actually equal to your maximum charge. Do you see why? It's the final charge that you build up to is going to be dictated by the voltage of the battery times the capacitance. So Q max is equal to the voltage of the battery times the charge on the capacitor. So in the end, you end up with that. Vmax times the capacitance when the capacitor is fully charged. In the end, what's the current when it's done? 0. All right. So last page. Voltage ends up building up. Wouldn't you agree? But what does current do? Current should decay away. And if you want to do the derivative and prove that, you can. Does that make sense? All right, so these problems tonight, I want you to get started right now. Feel absolutely free to use the notes and be looking off the notes as you work in your packet. But this is, once again, separation of variables practice. We're going to see this over and over again in circuits. That's it.